Bismillahirrahmanirrahim. Chapter 10. Rotation of a rigid object about a fixed axis. Right. So we need to firstly get to know few terms when we talking about rotations. Okay. So the terms that we need to get used is about the angular items or terms. Okay. Firstly is about angular position. So to define angular position for a disc, let's say for example, a reference line fixed in space is chosen. Okay, so this is our reference line. Okay, a particle at P is located at the distance r from the rotation axis through point O. Okay, so if we consider point P has r position from point O or axis of rotation. As the disc rotates, the particle at P move through an arc length, isn't it? The arc length is S, okay, on a circular path of radius R just now. The angular position of P is then theta right now. Okay, so the rotation is counterclockwise. So by applying approximation, okay, we know that theta is equivalent to the arc length over the r. This is actually by make use of sine theta. Alright, so this is from sine theta. Okay, whenever the theta is very small, more or less to theta only. Whenever the theta is very small. Okay, so the equation of sine theta equivalent to S over R is simplified to equivalent to theta only. That is how we manage to get this one. So theta is equivalent to S over R. To know the arc length, the linear displacement of the point P, okay, throughout the motion covering the theta in terms of angular position is equivalent to R theta. Right. So circumference, okay, for a circle is equivalent to 2 pi r, which equivalent to 360 degree. This correspond to, okay, 2 pi r over r, which is equivalent to 2 pi radian. Okay, so one circle is 360 degree is equivalent to 2 pi radian. Okay, so this is conversion factor, right? You may directly use your calculator. No need to memorize this one. Now, let's continue to angular speed. As similar to the linear speed, okay, angular speed is defined as change in position, okay, angular position over the time taken to have that change. That is average angular speed. Alright, and when we talk about delta theta, it means that theta final, okay, minus theta initial. Right, so how can we visualize this? Okay, so let's say our object, okay, is placed at point A at T initial. Okay, at T initial, the object is at point A, which having theta initial from our reference line, which is x-axis here. Okay, then the object is moved to point B, okay, circular or angular. Okay, the object displaced in terms of angular displacement to point B, where now it has theta final, okay, from the reference line. So from point A to point B, okay, the change in angular position is theta final minus theta initial. At any instant, still, okay, the object has R position from the origin or axis of rotation. So this is actually the omega that we are talking about. Okay, the omega direction counterclockwise, and it's positive when it is counterclockwise. If we're talking about velocity, if we're talking about speed, doesn't matter, the direction is not considered. Right, so this is talking about average. Okay, when we have average, of course we also have to recall about instantaneous. the instantaneous angular speed, okay, is defined as the limit of the delta theta, whenever the t is approaching 0. So it's equivalent to d theta over dt. The unit for the angular speed is radian per second, or we also can put it as per second. Okay, average and instantaneous angular acceleration. So when we have omega just now representing the angular speed, okay, we also have its acceleration, right? If the omega is keep on changing. So alpha here is known as angular acceleration. So we have alpha average, angular acceleration average is equivalent to change in angular speed over the time taken to have that change. And when you have alpha average here, okay, you have the unit of it is radian per second squared. Talking about average, a pair of it must be instantaneous. Okay, instantaneous angular acceleration is defined as limit for the delta omega whenever the t is approaching 0, or it's equivalent to d omega over dt. So we can visualize this is actually a similar analogy to have theta as the x compared to the linear displacement. Okay, omega, this is angular. If we compare to the linear motion, it's similar approach or item used for v, velocity or speed. Okay, and alpha is the item referred to the acceleration or e. So the direction of the angular vector. Okay, so rotation just now, okay, from point A to point B, right, which is counterclockwise. Okay, the omega is counterclockwise. If the alpha is positive, okay, here we have positive omega, right? If the alpha is positive, this is also the direction of alpha. Okay, so actually this is in terms of 2Ds where we consider x and y. The direction of omega and alpha is not within x and y axis or plane. Okay, it's actually on the third dimension, which is on z. Okay, which is on z, right? So if we are referring the rotating axis here, this here, with the rotating axis here. So if the object is moving, okay, if our point view is here, okay, so we're going to see that it's counterclockwise, isn't it? So the omega can be determined by using Grab's rule, okay, where we are going to use our right hand rule. Okay, our right hand, okay, place your 4 fingers along the road or the axis of rotation, okay, grabs it, and your thumb will be pointing to the direction of your omega or alpha. Alright, how about if the rotation is opposite, which is this is counterclockwise, and here we have clockwise direction if we see from this point view, right? So from this point view, this is clockwise direction. So put your 4 fingers along the axis of rotation, the road, okay, grabs it. Your thumb will be pointing to the direction of your omega, okay, which is to this direction, right? But if we consider only 2 dimension, x and y axis only, okay, take omega in terms of counterclockwise direction as positive. Okay, if it is clockwise direction, then your omega will be in negative direction. Goes the same to alpha, okay? Alright, so alpha is defined as d omega over dt, right? if we want to have omega only, d omega, then alpha dt. So change in omega is equivalent to integration of alpha to the respect of t from initial or 0 up to t time. Okay, and omega is d theta over dt. So we are applying the same method. So d theta is equivalent to omega dt. So delta theta is equivalent to integration of, omega initial plus alpha t dt. For a rigid object under constant angular acceleration means that the alpha is constant. Okay, we may use this equation, omega final equivalent to omega initial plus alpha t. Theta final equivalent to theta initial plus omega t plus half alpha t squared. Omega final squared equivalent to omega initial squared plus 2 alpha delta theta. Theta final equivalent to theta initial plus half average, half omega initial plus omega final t. Right. So this is actually similar analogy to particle under constant acceleration in linear motion. Okay, so this equation is actually approximately similar to this. It's just that the term is different because this is referring to the angular motion. Alright, so the unit of this is radian per second. The unit for alpha is radian per second squared, and the unit for theta is radian. Right, so here we have V is meter per second, A is meter per second squared, and your X is in meter. But bear in mind, this equation only valid whenever you have constant angular acceleration. This is constant acceleration. Okay, only valid when you have constant angular acceleration. So example 10.1, rotating wheel. A wheel rotates with a constant angular acceleration of 3.50 radian per second squared. A, if the angular speed of the wheel is 2 radian per second at t equivalent to 0, through what angular displacement does the wheel rotate in 2 seconds? Okay, so we may have the idea this is a similar situation to our previous slide just now. Okay, so delta theta is equivalent to theta final minus theta initial equivalent to omega initial t plus half alpha t squared. So our aim right now within 2 seconds, right? How much, okay, is the delta theta? So substitute all the information. Okay, you will have 11 radian, or in terms of degree, this is 630 degree. Part B. Through how many revolutions has the wheel turned during this time interval? So, as we know, 630 degree is in terms of angle. We may put it or convert it into revolution. One revolution is equivalent to 360 degree. So, from here, okay, you will see you will have 1.75 revolution within 2 seconds. C. What is the angular speed of the wheel at t equivalent to 2 seconds? So, angular speed, we want to know what is omega final because this is the t. Finally, at t equivalent to 2 seconds, omega of it is equivalent to omega initial plus alpha t, which give us 9 radian per second. Suppose a particle move along a straight line with a constant acceleration of 3.5 meter per second squared. If the velocity of the particle is 2 meter per second at t equivalent to 0, through what displacement does the particle move in 2 seconds? What is the velocity of the particle at t equivalent to 2 seconds? Okay, so delta x is equivalent to v initial t plus half at squared. From here, you will see your delta x is 11 meter. And to calculate the v final, make use of this equation, v initial plus at. You will have your v final is 9 meter per second. Now, let's take a look on angular and translational quantities. So, let's recall we have the arc length is equivalent to r theta, right? to have V is the rate of change of S. This is equals to R d theta over dt. So what does that mean? We can have V is equivalent to, this one is omega. D theta over dt is omega, right? Okay, so we can have V is equivalent to R omega, simplified equation. Okay, where is V? Diagram here, we can visualize the T is here. So certain books, okay, will state this is tangential velocity or speed. Okay, so it has T symbol here, Vt. So it means that tangential, because all the time the V must be tangent to the position considered. Alright? The unit of the V is, this is linear, right? Meter per second. Angular and translational quantities still. Now, if we have change in the V, okay, to the respect of time taken to have that change, okay, the rate of change of V is equivalent to AT, tangential acceleration. Okay, so tangential acceleration is a linear quantity, okay, or translational quantity we call it. V itself is equivalent to R omega. So we will have d R omega over dt. Since the R is a constant, we may put it outside. So it's equivalent to d omega over dt. D omega over dt is alpha. AT equivalent to R alpha. The unit of AT is meter per second squared still, because it's linear. Right. Okay. So now let's take a look on this diagram. Okay. Our object is at point P. Okay. At this instant, it's experiencing AT just now. Okay. Bear in mind, it is in circular motion or angular motion, because it's rotating about a fixed point. Okay, which is point O, our axis of rotation. Okay, let's recall about circular motion. When you move in a circular motion or path, you will experience A, which is to the center of the circle. Still remember that? Alright, so that is centripetal or circular acceleration, which is the A that give us a feeling that we are going to fall into a circle. Alright, so this A is known as AC, centripetal acceleration, which is equivalent to the magnitude of AR. What is AR? Radial acceleration, but in opposite direction, right? So this is actually negative AR is equivalent to AC. Right, AC is always to the center of the circle. V itself is R omega, right? So now we can simplify the equation into R omega squared for AC instead of using V squared over R only. So what is the real one that experienced by object at point P? Okay, the real A that experienced by object at point P is actually a resultant A due to the combination of AT and AC. Okay, AT caused by the change in magnitude of the V just now. Okay, so how about AC? AC is change of the direction of your VT just now. Remember, the object has V. Okay, the object has V. The V might change in terms of magnitude. Okay, the V also keep on changing in terms of direction. When the position is here, the position considered is here, the V is in this direction. So the V has two things that might change: the magnitude and the direction. Changing in magnitude producing the AT. Alright, changing in direction, producing AC. And all the time, AC is equivalent to negative AR. What is AR? AR is radial acceleration. If we recall back, AR is defined as change in R, position vector. Okay, position vector over delta T. Because we also have another information here, right? Which is the R. At any instant, the object has R. This is R initial, okay, of the object, right? So, the real one experienced by the object is actually a combination of AT and AR or AC. Okay, that is how we managed to get this equation finally. Torque is actually a kind of a vector quantity. Okay, it's a measure of change in rotational motion of an object about a fixed axis. Okay, in simple, torque is actually tendency to rotate about a fixed axis. Okay, due to certain amount of force applied to our object. Alright, so let's say consider a wrench here. Okay, this is our fixed axis, okay, or the rotation axis. Okay, and here we apply the force. Okay, the force is having phi angle to the horizontal, right? So, and we know that the wrench going to rotate. Okay, the direction of the rotation that possible due to the force here is this one. Is about a fixed point or axis here. Okay, so the component of F applied here, okay, can be resolved into X and Y component. Okay, so for the X component is F cos phi, and for the Y component is F sin phi. For the X component, there is no torque, okay, produced, okay, with respect point O as the axis of rotation. Okay, but yes, there is a torque produced due to the F sin phi, okay, with respect to this as your pivot or axis of rotation. To calculate the torque produced by the F applied, okay, to the wrench here, you have two methods actually. Whether, okay, you resolve the F into its component and find the perpendicular distance to the F, which is this one, the R here, isn't it? This is the perpendicular distance. So method 1, okay, torque about point O is equivalent to F sin phi, this is phi, okay, times with the perpendicular distance, which is R. Okay, this is the first method. This is the second method, okay. Instead of resolving the F, okay, you may use the F applied directly. But first thing first, you sketch the line of action of it. This is the line of action of the F applied to the wrench. Okay, what does that mean by line of action? It means that if you shift, okay, the F, whether at this point or at this point, the vector F stay the same. The amount of it, the direction of it, okay, stay the same F. Okay, it does not give any changes to the F information. So this is the line of action for the F. Figure out one distance which having 90 degree to the line of action of the F. This D is making 90 degree, okay, with the line of action of the F. So the D is the perpendicular distance. How to have the D? Okay, you have phi here, so this is also phi, isn't it? Then make use of the R information and also the D. to figure out the D is R sin phi. So your D is R sin phi. Then from that, to calculate torque at point O, axis of rotation, our axis of rotation is point O, is the F times with the D, which is equivalent to F R sin phi. Torque can be calculated in either way. Method 1, resolve the force. Figure out force that causing the rotation and calculate it with or multiple with the perpendicular distance to the axis of rotation. Or method 2, do not resolve the force but draw a line of action for the force. Figure out a perpendicular distance from the axis of rotation to the force and calculate the torque by using formula of this. Similar approach, you will get similar results. So if you have more than 2 forces, okay, applied to your object, okay, what should you do? Okay, this is your axis of rotation. Okay, what should you do? You're going to calculate the net torque on your object. So the net torque going to be torque due to F1 plus torque due to the F2. If you have more than 2 forces, then you have to add up this item until finish. Okay, then for the torque due to the F1, if we see here, the possible rotation, okay, this is our axis of rotation. So the possible rotation due to the F1 is going to be like this, which is this is torque 1, okay, which is counterclockwise, it's positive. And possible rotation due to the F2 is this one. So this is torque 2, which is clockwise direction, which is negative. Okay, and it's already perpendicular distance, so no need to resolve anything. Okay, so our torque 1, this is in terms of vector, okay, our torque 1 is positive, okay, but our second torque 2 is negative. Okay, additional example 1, this is taken from other reference book. Okay, two disgruntled business people are trying to use a revolving door which is initially at rest, okay, in this figure. So this is our fixed point, right, or axis of rotation. The woman on the left, okay, exert 625 Newton perpendicular to the door and 1.2 meter from the hub center, while the man on the right exert a force of 850 Newton perpendicular to the door, 0.8 meter from the hub center. Find the net torque on the revolving door. So first thing first, okay, let's visualize, okay, the free body diagram of the door, where point O here as the hinge, right? So the woman going to produce rotation or torque, tendency to rotate about point O, okay, to this direction, which is clockwise direction, and it will give negative value torque, okay, due to the F1 of from the woman. Right, for the man, okay, the tendency to rotate or torque is counterclockwise direction, so the torque produced by or due to the man going to be positive. The net torque on the system is equivalent to torque due to the F1, the woman, plus torque due to the man. So remember, for the woman, okay, it has negative sign because the direction is clockwise direction, and there is no more sine theta because the R already perpendicular, okay, to the F1, goes the same to the F2, right? So F1 R1 negative plus F2 R2, and our F1 is negative 625 times 1.2. Don't forget about the negative sign. And our F2 is 8.5 times 10 to the power of 2 times 0.8. So our final answer is negative 70 Newton dot meter. What does that mean? Means that the woman, okay, is the winner. Okay, the woman going to open the door. Right, that is the meaning of our answer. So additional example 2, okay, a man applies a force of 300 Newton at an angle of 60 degree to the door on figure 8.7. 2 meter from the well-oiled hinge. So hinge will be our axis of rotation. Find the torque on the door choosing the position of the hinge as the axis of rotation. So first part, okay. So we have force applied here, right? So we are going to use, right, a resolving part of it, okay. So resolve the 300 Newton into X and Y component. The X component has no torque produced because it has no perpendicular distance. Okay, line of action is passing through the hinge, isn't it? Line of action for the 150 Newton is passing through the hinge. So it has no perpendicular distance. So the one that effective that causing the rotation is Y component, which is 260 Newton. And the possible rotation will be in counterclockwise direction. So 260 times with the perpendicular distance, which is 2 meter, give you this amount. Or method number 2. Method number 2, okay, where we are going to use line of action for 300 Newton. Figure out the perpendicular distance, okay, from the line of action of the force towards the axis of rotation. So our D will be R sin 60. So from that, torque produced at point O is equivalent to 300 times with a D. So the D itself is R sin 60. Will give you the same answer. Okay. So now, part B as your homework. Alright. You will solve this and upload your results or solution to our Telegram discussion.